Okay, so hey everybody, this is Mr. Bells again. This is a video for data analysis. This is on an introduction to this this new symbol, it's actually a number E. So I want to give you a quick little rundown first. You guys all know pi, and pi is a number 3.14159 that comes from circles. So that if you take any circle ever, and measure the circumference of it, and then take whatever that number is, and take the diameter, which is all the way across the circle, and you divide those two numbers, this 3.14159 number keeps coming into play. So it's not like we made this thing up. We just went and looked at all of these different circles and did some measurements and cut it across and did the division and realized, hey, no matter if the circle's this big or the size of a dime or a helicopter landing pad or the circumference of a planet, which aren't perfect circles, but we're gonna call that good enough for right now, that all of those times we get this number 3.14159. Well, in exponential functions, when we do something called continuous compounding, we get this number. So the maximum value that a continuous compounding can get to is going to kind of level off. It's going to have an asymptote. We've talked about a lot of asymptotes at this number 2.71828, and we call that number E. So it's a lowercase e, and we're going to talk about how we use E and where it comes into play on some of these problems. Okay, so I'm going to give you a quick rundown of where that E came from first, and that. So again, just gave you the quick little rundown on this, right? Pi is circumference divided by diameter equals pi every single time. And you're like, wait, what? I thought, huh? Well, watch. C equals 2 pi r. That's the formula you guys know, right? Awesome. So I'm going to divide this side by 2 and by r. Right? So that'll kill that and that'll kill that. So if I go over here, 2 and r are both on that side, you can see that pi equals circumference divided by 2 radiuses. Well, 2 radiuses is diameter, so that's why pi equals circumference divided by diameter. Okay? So how do I get this E thingy? First off, E is a number. I shouldn't say equals because it's an irrational number. It goes on forever and ever and ever. 2.71828 blah 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 stuff after that. Okay, so how does this come into play? It comes into play when you take the number 1 and you add 1 over. We're gonna approximate this right now, n to the n power, and we're going to have n approach infinity. We're going to have that compounding. So remember, if it was it's kind of like I'm going to do $1 and I'm going to get 100% interest. So this is the dollar right there. This is the 100% interest, and n is the number of times a year I go ahead and plug that in. So watch. So I'm going to do this on this calculator. I think it's charged up a little bit more. I'm going to make sure that I charge it again in the thing. So I'm going to do parentheses 1 plus 1 divided by, let's do quarterly first. Do quarterly raised to the 4th. And all of these are going to be 1 year. So technically you can just multiply that by 1 up there in that exponent spot. By 1 for these things, and I hit enter, and you can see I get the number 2.444. I'm like, okay, well, what if I do it monthly? So 1 plus 1 divided by 12. Oops, sorry, I got to put parentheses in there first. Parentheses 1 plus 1 divided by 12 raised to the 12 times a year. I get this number 2.61. Well, what if we make this even bigger? Let's say we do it every day. 1 plus 1 divided by 365. I forgot to do it again. So if you forever forget to insert stuff, this little button right here, INS, see that? INS, that'll insert. So I just hit that second and insert, and I can put my parentheses in there, then I don't have to retype it. And then close parentheses and raise that to 365. So remember, this is really me investing $1. I'm getting 100% interest. I'm dividing that 100% interest up over 365 days and raising it to 365 technically times 1, right? Because I'm only doing this for 1 year, looking at it. And you can see I get 2.714. Ooh. So what I want to do right now is this. I'm going to show you one more of them. So instead of 365, let's do it like, I don't know, 1,000 times. So parentheses 1 plus 1 divided by 1,000. So basically just under 3 times a day. Raised to the 1,000. And you can see that when I did it quarterly, which was right up here, right? It turned into $2.44. I did it monthly, it turned into $2.61. I did it daily, it turned into $2.71. So it's increasing every time, but it's not increasing by that much more. There's a limit to how much it can grow. So this was at 1,000. So what we want to do is we want to take and see if we can go, well, what if I do it every minute or every second or every billionth of a second? Well, what I'm going to do then is I'm going to look at making that a variable. So I'm going to put it in as this, parentheses 1 plus 1 divided by x raised to the x power. And I want n to get bigger and bigger and bigger. So you can see right now, I'm going to show you a couple things. I'm going to show you I'm going to show you zoom 6. So there's my graph. All of this stuff over here doesn't have any impact on the problem because those are all negative numbers. Okay, so I'm going to change my window. So my x min is 0. My y min is 0. My y max is going to be 3, and you can see this. You can see that as I compound it more and more times, this is 1 time per year, 2 times per year, 3 times per year, 4, 5, 6, 7, 8, 9 times per year, that it's kind of tapering off, okay? That looks like maybe there's an asymptote going on. So I'm going to change my x max to 50, hit graph, and it still looks like there's kind of an asymptote there. So I wonder what that asymptote is. So I hit the trace button, and you can see I'm at 2.66, 2.67, 2.6, right? And those numbers down there keep going out that way. And you guys know I already got it to, I did it to 1,000. Right now my x is only at 32. So let's do this. Let's make my x max 10,000. Now I hit graph. And that same graph that had the little bump up and then the straight line across looks pretty flat. Yeah? Okay. So now I hit trace. Now I'm at 5,000 times a year, and you can see I'm at 2.718. Ooh, that looks just like that E thing that we said. So I go out here to 6,000, 7,000, 8,000, 9,000 times a year. This is 9,166 times a year. I got 2.718, and you can see that I got this. Okay? Now it's going to have some glitchy, numbery rounding things as we go. But 2.718, and we said it was going to be a 2 right now, right? 2.71828. So watch this. I'm going to go back to my window. I'm going to change this to x min of 0 and x max of, let's go 50. And my y2, I'm going to put the actual graph of E. And you can see my division symbol, there's a little lowercase e. That's one of my e's. And then right over here, this is the one I'm going to use when I'm doing actual e to a power, which is what's going to be coming up in most of our story problems. So I'm going to use this one this time, but lots of times I'm going to use e to the x so that I know that I have an exponent. Okay, so this e is in the blue, so I'm going to hit second function and that e, and you can see that it's going to graph e. And when I hit graph, there's the graph of the function, and then here's e. and you can see that the blue line is going to get closer and closer and closer to the red line every single time. I hit trace. This is my 1 plus 1 over x to the x graph. I'm going to hit my up arrow, and it says that it's E, and you can see that there's my 2.71828. Okay, so that was a lot of information just on where this E occurs from. So again, it occurs when the number of compoundings, instead of doing it 4 times per year or 10 times per year, I continuously do it. So continuous compounding. Okay? And if you want fancier videos on that, you can look up E and see some of the other people that have done stuff on it. But what we're doing here is totally good. Okay, so question is can I simplify expressions like this? Can I use E and do regular math stuff? So yes, E to the 4th times E to the 8th does equal E to the 12th. Now, of course, this isn't an X, right? This isn't a variable. It actually is a number. So if I wanted to know what E to the 12th is, I could actually do E to the, and notice I used this one this time because I'm going to raise it to a power, E to the 12th. It'll look just like that. I hit enter, and I can see that it's 162,754.79. Okay. Whoa, that's pretty big. It is, because remember, E is 2.71828. So watch. So I'm going to do 2.71 raised to the 12th, because that's kind of like E, right? It's a little smaller than E, but it's kind of like E. And you can see that the result is a little bit smaller than what I got that way. Okay. So now I'm going to do this. Well, what happens with this? Well, this 4th power goes to both of these things. So I'm going to have 3 to the 4th power. 3 times 3 times 3 times 3. Well, that's 81. E, right? E. And now what happens when you do a power to a power? Well, you multiply those. So 2x times 4 is 8x. So I'd have 81 e to the 8x. Okay? And that would be a simplified form of that. Now, what about if I have something like this? Can I still do all of these things with it? Absolutely, I can do that. Remember, powers, 2 powers, I multiply, right? And then what if I have just bases? Well, I add those. So this would be E. 2x plus 5x is 7x plus 7. Now, I can't put that 7 with those letters the same way I can't, you know, if I said, well, what's 3x plus 2? Well, 3x plus 2 is 3x plus 2. I can't add numbers to letters. Okay. So then I'm going to look at these ones. I'm going to say, well, is this growth or is this decay? Well, this is the first time I'm showing you this one from this situation. But you know that the base, right here, the base, technically, watch. 1 times e to the 0.2x. So this would go through 0, 1, because it's the initial starting amount, right? Number that's in front of it, which was just an implied 1. E is the number 2.71828. 2.71828 is bigger than 1. So if this is greater than 1, it's going to grow. So you know that it's going to go like this. Now, 0.2 per x means it's not growing very fast. It could be really slow on that growth, but it's still going to grow. Now here, what's the difference over here? When we have this, e to the negative 6x, negative exponents, right? Negative exponents. Really what that means is that I have 1 over e to the positive 6x. So if this thing's growing, if this bottom's getting bigger and bigger and bigger, but it's in the denominator, then this is actually going to decay. So I'm going to show you both of those on here. So I'll go ahead and take your calculator, turn it on, clear and clear. So the first one I'm going to do e to the 0.2x, e to the 0.2x, and my window, I'm going to do 0 to 10, and 0 to 10. Okay, and I'll hit graph. And you can see that that's definitely growing over time. However, this was 0.2x, right? E to the 0.2x, so that's growing pretty slow. So let me show you e to the regular 2x, just so you can see that it's still going to grow, but it's going to grow faster. Ooh, is that a lot faster? Okay, so 0.2x, pretty slow growth. 2x, super fast growth. Okay, so now let's try it the other way. Let's try it with a negative exponent. So e to the negative 6x. And I hit graph. And you're like, wait, where is it? Oh, look, it's way down here. It's tiny. Do you see it? It's so tiny right down there in the bottom thing. So let me show you the other side of this. So let's go negative 10 on my x-axis. So I'm going to look to the left. And hit graph. Now you can see whoosh. Now that's pretty stark decay. Let me show it to you with it a little slower going on. So second function e to the negative 0.6x, right? This should be slower, but still going to be decay. Again, decay because it's a negative exponent. And I hit graph, and now you can see that it definitely does decay. It's just decaying at a slower rate than the really sharp 6 to the x one. Okay. So we've seen how to work with this E thing. Now let's talk about an actual problem. So Johnny invests $12,000 at 6.5% interest, compounded continuously. That means that he doesn't get paid interest at the end of 1 year. That would be annual. He does not get paid interest 4 times per year. That would be quarterly. He doesn't get interest paid 12 times. There we go. 12 times per year. That would be monthly. Or daily, which would be 365 times a year. He's getting interest compounded continuously. Continuously means that it's happening not every day or hour or minute or second, but every billionth of a second. Bing, 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 bing. It's still getting that interest paid on it. But remember, when we're doing it every second, we're only getting that tiny, you can't even see the difference between that gap in my fingers, right? It's so much smaller than that. Tiny bit of interest paid each time, and you're just paying that millions of times per year. Okay? So there's the nice thing is that this this compound interest formula, A equals P times 1 plus R over N to the NT, when this N gets close to infinity, right here, we don't have to use this formula anymore. When we're going to do it an infinite number of times or continuously, we actually can use this new formula right over here, because we know that 1 plus 1 over n to the nth power equals this E. And this kind of takes the place, this right here takes the place of doing this one at really big times. And this is a lot easier to put into your calculator. So how do I do this? It says $12,000. Well, that's my P, that's my principal. So I put in 12,000, right? At 6.5% interest. Well, that's an R, that's an interest rate. Oops, I got to have my E. So I do second and this ln key right down here. That's where my E is when I raise it to a power. Okay. Interest rate, 6.5%. Remember, I have to do it as 0.065. Do not put it in as 6.5%, or you're going to get a DIMS answer. You're going to get something that doesn't make any sense. If it did, it'd be awesome if it really did. But it doesn't. You just become wealthy within a matter of a year or so. So it doesn't. So I got that 0.065 times 17 because it was for 17 years, and I hit enter. And it says that my $12,000 will become $36,230.69. $36,230.69. That's what happens if it's compounded continuously. Okay, so let me show you annual, just so you can see that continuous makes more than annual. So annual means I have it 1 time per year. So that would be 12 thousand, right? Times 1.065 raised to the 17 years, $35,000, where now I get $36,000 because the interest was compounded continuously. So I made almost $1,000 more because they paid that interest that fast. Now, of course, in the olden days when they actually had to figure this stuff all out by hand, there's no way that they could compound interest continuously because it just takes too much time. Now computers can do it, right? They can do billions of calculations a second. It's not a problem. We can do that. Okay? So what I want to do is just kind of look at, and I did a little bit of this already before, look at the graph, right? But I also want to look at something called a table. So I'm going to go ahead and put this one into here so that you guys can see this. My y equals clear. I'm going to do my principal, which was 12,000. I'm going to do my E. I'm going to do my interest rate, which was 0.065. And then I'm going to use X for my number of years. Okay? So before I hit graph, because I want to set up my window that makes sense, and it's going to be tough for you guys, right? Mentally to be able to process this all out. But X is years, Y is dollars. X is years, Y is dollars. So in this case, going back 10 years in time doesn't make any sense, so I'll start at 0, and I'm going to go out 20 years. Y min 0, Y max. Remember, I'm already starting at 12,000, but I know that that's going to go way up. So I'm going to put it at 100,000, and I want you to see the graph. Okay, so you can see that it's slowly growing over time. But remember, I just did that out 20 years. So let's go 30 years. 30 years. So I changed it to 30 years. And you can see that, ooh, see what happens in those next 10 years? It starts growing up a little bit faster. Okay? So now I'm going to show you the table. So how do I get to the table? See, there's this button right here that says table setup, and this button right here that says table, and they work in unison. So I'm going to go second, table setup, and this says, well, what do you want to start it at? I'm going to start it at 0 years, and I'm going to have it go up 1 year at a time. Okay? Now to see the table, I'm going to go like this, second and graph, which pulls up the table. So this shows you at time 0, that's your initial amount, $12,000. After 1 year, I'd have 12,806, or down here you can see the actual number, 12,805.90829, or at least closer. Remember, this is rounded, this goes on infinitely long, and so on down the line, and you can see how that number is increasing. So you can use the table to figure out some of these values going up, or you can use your graph to be able to do it. So let's say that I wanted to ask this question on this particular problem. When will it reach $100,000? When will my $12,000 investment reach $100,000? Well, technically that means that that's my amount, that's my ending amount here, is equal to P, which is 12,000, E to the RT. So I'm trying to solve this equation. 100,000 equals 12,000 E to the 0.065 times T. I'm trying to solve this. Again, I don't know how to do this yet. We haven't talked about how to solve this algebraically. It involves something called logarithms. And this one, because it's an E, involves a special type of logarithm called a natural log. But I can do it on my calculator still. So we're going to go here. I'm going to go ahead and put in 100,000 like this. And I'm going to show you two ways. Remember last time we just guessed and checked on our home screen. We put numbers in until we got to something close to it. Well, I'm going to use the table this time instead of just guessing and checking, because the table shows me stuff pretty quickly. So second, and there's my table, right? And I want to get this until it gets to 100,000. Oh, do we see it? Right there. 32 years, it's 96,000. At 33 years, it's 102,000. So it looks like somewhere between the 32nd and 33rd year. That's an approximation, right? If I want to know it exactly, I'm going to go to my window. I know it's between 32 and 33 years, so I'm going to X max out at 40 years. My Y max is now going to be 150,000 because I want this to be higher than where my line's going to be at. See, there's my 100,000. I hit graph. At some point, this thing's going to grow and grow and grow past the 100,000 mark. I want to know what that point is. Second trace, number 5, enter, enter, enter. And you can see it says right here, 32.6. 32.6. Okay, so hopefully all this stuff has helped you tremendously in terms of understanding what it is, where it comes from. You've gotten a lot more practice using this calculator, and then you've taken good notes on this stuff. This is Mr. Bells with where did E come from on exponential functions. We'll talk to you later. Bye.